Welcome back. In this video, we'll be taking a look at currents and Joule heating in current carrying wires. Let's take a look at the problem statement. The current density magnitude in a certain circular wire is 2.75 times 10 to the 10 amps divided by meters to the fourth power times r squared, where r is a radial distance out to the wire's radius of 3 millimeters. The potential applied to the wire end to end is 60 volts. How much energy is converted to thermal energy in 1 hour? This problem is asking us for energy loss in a certain amount of time through a current carrying wire. Now, physically, what's happening? Why is there energy loss in the first place? And the reason this is happening is because when you hook this wire up to two ends of a battery and you have a voltage difference across it, the electrons are going to want to start to move, to accelerate to one direction. But they don't move uniformly, and they don't accelerate. In fact, what happens is they are moving in kind of all different directions with an overall flow in this direction, but they are colliding with one another at a very high rate. And as they do so, they undergo inelastic collisions, giving off energy, and that energy is heating up the wire. And that energy loss is called Joule heating or resistive losses. And that's what we're asked to find in this problem. So you kind of have these electrons moving in all different directions, colliding. And that's the picture you should have in your mind, that they are undergoing a lot of collisions as if they were bumper cars with an overall motion in the direction of the current. What we're going to start with is the definition of energy loss per time, which is also known as power. So let me go ahead and write that down. And I'll say that the change in energy per time, which I'll say energy of heat per time, is defined as the power. And for current carrying wires, the power that's dissipated over the wire is equal to the current traveling through the wire times the potential difference across the ends of the wire. So if you want to find the total energy loss in a certain amount of time, you can let's just put the dt on the other side of the equation, and we can integrate both sides. And so the left-hand side is trivial, and that just gives that the total heat lost, the total energy loss equals the integral of the power over time. In the situation where you have a constant current and a constant voltage difference across the ends, the power is constant as well, so you can take it out of the integral. And so in the case where the power is constant, as it is here, typically that's the case when you have constant currents, then you can take p out of the integral, and all you're left with is, let's say, p integral dt, which is just p times the total amount of time. And here we are given the total amount of time, it's 1 hour, so all we have to do is find the actual power that's dissipated at any given time, and that's going to be a constant number. All right, so if we have the power, we know it's equal to the current times the delta V. Well, we're given delta V, so that's trivial, but we need to find the current that's actually traveling through the wire. We're given something very close. We're given the current density, and we know that the current density is defined as a current per area. So let's start by writing that down. The total current is a current density times the area. Well, that would be true if the area, or if the current density were actually constant. In this case, the current density is not constant. It depends on where you are on the wire because it has this R dependence in there. So if it's not constant, in fact, we have to integrate the current over the wire. When it's constant, you just get this because you can pull J out, integral dA is A. But in this case, it's not. So we have to perform an integral. So the first thing we need to do is perform this integral. And what I'd like you guys to do on your own is, before we do that, though, let's get a kind of a visualization and a feel for what the current density actually looks like in this wire. So let me just draw kind of a cross-section of the wire here. And I want you to do the same on your page. And in that cross-section of the wire, I want you to kind of shade where, using a shading, kind of figure out where the current is very dense and where it's not as dense. So basically where you think it's going to be dense, shade it much, much darker than other areas. For example, if the current density is high in the center, you would kind of put it like this and then kind of space it on the outside. On the other hand, if you think that the current density will be very high on the left-hand side versus the right-hand side, it would look like this. Right, so do that real quick, get a kind of feel for what the current density looks like. And you can start with this formula that tells that the current density equals this constant times r squared. So take a minute and do that now and pause the video if you need to. Since the current density is proportional to r squared, let me draw a cross-sectional area here. Since it's proportional to r squared, then that means that the current density at the very center is basically 0 because r is 0. And then as you move radially outward, the current density increases. So kind of we have something that looks like this. It's going to be very dense on the outside. but not as dense on the inside. And this is interesting because a lot of wires actually have this type of thing going on. This occurs in particular when you have alternating currents in wires, which we may or may not have talked about yet. But when you have alternating currents in wires, there's a phenomenon known as a skin effect, which I'll write over here. The skin effect, which because of magnetic fields and what's known as eddy currents, it causes all the current in a large wire to actually be only transmitted on the edges. And that has to do with the fact that it's alternating current and there's induced fields. So that's not relevant in this situation, but I just want us to be kind of aware of the fact that this picture we have of uniform currents traveling down wires is not always the case. And in fact, in most actual applications, current may have a density that's not uniform. In any case, moving on, let's solve the problem. We want to solve this, we want to evaluate the integral, but we want to write it as an integral over some variables r and theta. And so what I want you to do on your own real quick is to rewrite this integral as something over an integral of j and dr d theta. And there's going to be some factors in here from the change of variables. So if you're not sure what those are, maybe go back in your vector calculus book and recall what those factors are. Get an expression for the integral, and if you think you can integrate it, go ahead and integrate it. And we'll come back in a moment and solve that integral. When changing from Cartesian coordinates to polar coordinates, there arises a factor of r due to the change of variables. And if you're not sure why that's the case, you can check in the posted solution or any vector calculus book, and it'll explain where that factor comes from. So now that we have that integration factor, we can carry out the integral because now everything's going to be in terms of r's and thetas. So let me rewrite this as two separate integrals, one over the radial component and one over the angular component. So the radius extends from 0 to r, which is basically integrating from the center to the outside of the cross-section of the wire. And then the angle extends from 0 to 2 pi, which is integrating all the way around. The current density is 2.75 times 10 to the 10 times r squared. And then you also have this extra r from the integration measure. And then finally, you have your dr and d theta. And so you can carry this out over each variable separately. I would recommend carrying it out over r first and then over theta. Those integrals are not hard. You can find the answer, and you can get that numerical answer. You can check it in the posted solution. I'm not going to write it down, but I'll just put that there. So that's our current. Now, what we're looking for in the problem is how much energy has been lost when due to the Joule heating, the resistive losses, in a period of 1 hour. So we had an expression for it down here. The total energy that was lost as heat equals the power times the amount of time over which it was heated. We have an expression for the current now, so we can actually plug that in for the power. So finally, solving the problem, we have that the energy lost as heat is the power times the amount of time. And the power in this case is I, which you'll find right now, times the voltage difference across the wire, which is 60 volts. And then finally, times the time, which is 1 hour. And you can solve this on your own numerically. It's straightforward. Just be careful about the units because they're not in SI units right now. When you get a numerical answer, you can check it with the posted solution. So let's stop there and let's go ahead and summarize. In this problem, we were asked to find the thermal energy loss in a wire given the potential difference across the wire and the current density. The first thing we did is we found an expression for the thermal energy loss in terms of current, voltage difference, and time. Then, because we didn't have the current, we found an expression for it as an integral of the current density over the cross-sectional area, being careful of the change of variables to polar coordinates. Finally, we evaluated the integral and solved for the dissipated energy. And so that's it for this problem. Please leave comments and questions if you have any on the link attached to the video, and we'll see you next time.